Hi, this is Mr. Yeager doing a lesson for circular motion for regular physics. There's another one out there for AP physics. It's barely different, but there's one little less thing we really worry about in regular physics doing circular motion. So we are looking at, obviously, motion of an object that is moving in a circular pattern. And we are primarily focused on the velocity, the acceleration, and the net force that acts on this object as it moves around and around in a circle. So this is another form of what we call translational motion. So in a way, it's related to linear motion. This is not rotational. It's not spinning in place. So we still have a lot of things that's related back to kinematics. But you'll see in this unit, we'll be doing plenty of free body diagrams in addition to kinematics to figure out the problems here. So if we start off with this particular setup, you can see the girl swinging an object around and around and around. We've often called this force to make an object move in a circle a centripetal force. Okay, a centripetal force. The thing is, sorry, let me try to figure out something here. I'm trying to get this back. Sorry about that. With the centripetal force, that's always been called the center-seeking force. That's obviously what you see down here. Centripetal force, centripetal means center-seeking. The thing is, there's really no such thing as centripetal force. We want to identify what is actually making it go in a circle, and that would be the string that this girl is using. So it would actually be a tension force that's creating this center-seeking force. All right? But this object's moving around and around in a circle, and we want to focus on, again, which direction would velocity be, which direction would the net force, and which direction the acceleration would be as we do these problems. But you're going to see we're going to include regular forces in this as well. Excuse me. So, again, like I said on the prior page, there is no real thing called a centripetal force. Okay? Instead, we are always going to be calculating what's simply the net force that's acting on the object. The net force is acting toward the center. All right. So what I really mean by that is we're not going to sit here and draw a free body diagram and have a force called F of C. Okay. If you do that, that's going to be marked wrong. There is no such thing as centripetal force. Just like we've never drawn or written F net as part of your free body diagram, that would also be wrong, okay? We only want to put down the real forces. We want to identify what is the real force that's causing this center-seeking motion, this circular motion. And it can be any force that we have done so far. I only have a few less listed here, tension applied and gravitational, but normal force and frictional force, we will see, also can be center-seeking forces. So again, we only look at what's called uniform circular motion. Okay, it's often abbreviated simply as UCM. Nothing too special there. All right, and what that means is that the object will be moving with a fixed speed. A fixed speed around the circle. So it will have a constant speed in addition to a constant radius. We'll see how these affect the velocity and the acceleration, everything basically. All right. But obviously, there's going to be plenty of questions of, but is it accelerating? If you're spinning something around at constant speed, is it accelerating? So think about that. What would cause, is it accelerating? What does acceleration again mean? All right. And so, here's a little diagram of, obviously, centripetal force. Okay. Without this center-seeking force, this object will keep going off in a particular direction. All right. The thing is, in my second diagram, I have a little a little object blocking the tennis ball, and so that is creating this center-seeking force, a force pointing toward the center of the circle. If this keeps on moving around and around and around, it'll always keep pointing toward the center of the circle. All right. If there is no force causing it to move in a circle, that object will move off in a straight line. This is Newton's first law. If the object will keep doing what it's doing unless acted upon by an outside force. Okay? So we need some sort of force to make it keep on turning it, constantly changing its direction. Excuse me for my cough. Alright. Now, this is kind of just another kind of general situation. Alright. Again, think about if you're making this turn around a corner. Okay. Think about which way your body will lean. It'll always lean toward the outside. It'll always lean towards the outside. And so this slide, really, I'm trying just to introduce that there is this center-seeking force, but there must be some sort of opposite force acting against it. This is related to Newton's third law. All right? If something is pulling you in, technically something is pulling you out. And we call that outward-seeking force centrifugal force. You probably have heard of centrifuges. Obviously, these things that spin and obviously separate out maybe different blood components or any sort of material. All right? But the whole idea is we use that centrifugal force to obviously pull things toward the outside. And that only occurs because of Newton's third law. If there is a center-seeking force going in, there must be an opposite and equal force going outwards. All right? And this will come up in a lot of different problems we try. Not necessarily, again, the word centrifugal, but the fact of what effect will it have as a result of this turn. All right? And again, your body wouldn't keep on moving with the car unless, obviously, the car is pushing back against you, which is what it does. Okay? If there was no car, if the door was open, you'd fly straight off outside the car. Okay? You'd fly in a straight direction of the last direction of motion. Okay? So obviously we need that normal force from the car side to keep you moving with the car itself and continue moving in a circle. All right? So again, a little bit strange. I'm introducing terms, what obviously centripetal and centrifugal mean, but there are certain physics classes that never mention them. Okay, they're more of an idea, an abstract going, okay, what does this refer to? It's something center-seeking or away from center-seeking. All right. So now we get to these more specific questions about, okay, I already said this. There's roller coasters will move at a constant speed, but will their velocity change? Okay, and obviously, as it says here, their velocity does change. Why is this? This goes all the way back to Unit 1. What does it take to accelerate an object? Acceleration is not just velocity, but also direction. Okay, or I should say speed. All right. Acceleration is speed and a change in speed and a change in direction, or a change in velocity and a change in direction. Well, the velocity, the speed itself is not changing, but the direction is, so therefore we are accelerating. That will be a classic question. Any object going in a circle is accelerating, is changing velocity. There you go. Okay? It has direction and speed related to it. All right? So, this leads us to finally our mathematics. Again, like I said, we're going to be doing speed, acceleration, and force. All right? The thing is, we also have to, sorry, I want to check something real quick. Yep, that's it. Okay. The thing is, when we measure speed, if you think about what speed is, it's distance over time. But when we do experiments on circular motion, it's not going to be easy to measure the speed of, one circle. Okay, somebody could be swinging something very quickly around, and you're not going to be able to measure that quickly enough. All right, so it's difficult to measure the time that maybe the object swung from the top to the bottom. That's not going to be easy. So instead, we measure the time that it takes for one revolution, and this is called the period. And this will come up again in another unit. Actually, I think in 2 units later, next unit when we do energy. All right, the period. The period, denoted capital T, not lowercase t for time, is the time for one revolution. So period equals time over one revolution. Okay, time over one revolution. All right. So what we do here is we might go, okay, you do 10 revolutions in 5 seconds when you swing something around and around in a circle. What would the period be? Well, period would be 5 seconds, 10 revolutions. So how long did it take each revolution? 0.5 seconds. And we don't write revolution, we just write seconds. Period is a measure of time. Revolutions is a counting number, we don't include that. All right? So be very careful. One of the most common mistakes I see people do is they go, period equals 10 revolutions over 5 seconds, it equals 2. That is really, really wrong. Okay? It has to be time over revolution. So be careful of that, because you will see some practice problems. We actually will do one together where I give you how many revolutions occurs over the amount of time. So we need to inverse that. We need to inverse it all the time. All right? So finally, that leads us to speed. Okay? And so as you can see here, speed, we already know, is distance over time. But the thing is, we're doing a circle, so distance becomes circumference. And the circumference of a circle we know is 2 pi r, 2 pi times the radius. All right? And so that leads us to the formula. This formula at the end here, this is velocity. Velocity equals 2 pi r over the period. 2 pi r over the period. Now, I get a lot of people that ask me, when I solve this, don't tell me velocity equals, 4 pi meters per second. I don't like that. Okay? In physics, we always multiply everything out. So make sure you multiply out 4 times pi, which would be something like 12.4. Okay? So don't leave answers with a pi in the answer. That's not going to be accepted. You're not going to see that on any multiple choice or anything else like that we give. All right? But there's your formula. Velocity equals 2 pi r over the period. Okay? And this r is the radius. T, big capital T, is the period. All right? As for acceleration on a circle, we need a different formula, and we do this one right here. Acceleration is v squared over r. So a lot of times you might have to solve for v, and then you square it and divide it by r again. This radius is the same radius we used the first time. All right? If we use a radius of 5 meters, when you do velocity equals 2 pi r over t, r equals 5 meters. Then when it asks you to do the acceleration, this is also 5 meters. Sometimes I have students that ask me, oh, I need another r because I'm solving for acceleration now. No, it's the exact same radius. Don't overthink the problem. Okay? This formula over here is just another way to write out acceleration. I don't give this one on a test sheet. Just understand what they're done here is they plugged in 2 pi r over t for velocity and squared it. And so this is 4 pi squared r squared over t squared. The thing is, if I divide by r for acceleration, if I change this to acceleration now, one of the r's cancels out. So these two formulas are identical. I pretty much never use the second formula. I almost always end up solving for v and then plugging it into this v squared over r formula. You are more than allowed to use the second formula if you want. That's all up to you. Okay? Both of them should get you the same answer though. All right? So we talked about velocity and acceleration. And there's one thing I've missed here, but we'll look at it in a second. This slide you can see says acceleration occurs in the same direction as force. Okay? So the other questions we love is, which direction do velocity, acceleration, and force point? Where we already said, let's say our object's at the very top here going clockwise. Okay, around and around. That would mean force is pointing towards the center. The net force always points towards the center of the circle. Always. The acceleration will always point in the center of the circle. So, and that's because, again, think about it. An acceleration is created by a net force. So the acceleration and net force always point toward the center. Okay? Always towards the center. Net force and acceleration. Okay? Which way does the velocity point though? And this is something we brought up back in equilibrium in unit, what was that, 3? Okay, when we started doing forces, I guess unit 4, okay, when we did forces. Which direction is this object going at this moment in time? That would be tangent to the circle. And since it's going clockwise, it's going to the right. So velocity is always tangent to the circle. Okay? So velocity is always pointing tangent to the circle. All right? So we've gone over the main formulas for velocity and acceleration. We haven't hit net force yet. Okay? And we've gone over what directions these different quantities go. Net force and acceleration always towards the center. Velocity always tangent. Okay? And again, that's why if it ever asks, when you release the object, where will it go? Off in a straight line, tangent to its last motion. Okay? That's basically what we're looking for. All right? And so, we get to some of these other little questions here. Can you go around a curve with a 0 acceleration? The answer would be no. Okay? No. Why not? Because it's changing direction. Even though the number might stay the same, the magnitude might stay the same, the direction is constantly changing. For this object here, acceleration would be pointing down there, but be pointing left when it's on the side at the 3 o'clock position. Will it have a constant acceleration? Again, no, because it changes direction. Don't get confused with the number staying the same, with that being simply what acceleration is. Remember, acceleration is a number and direction, so this is never true. Okay? It is never, ever true. And it has to do with the direction. Always, always, always. We're always changing the direction. So acceleration is always changing. All right? As for the net force, we have to be able to pay attention to this. And this came up with Atwood machines too. We kind of define what is positive and negative forces. So the net force, as stated at the top, is always pointing toward the center. Okay? Always pointing inwards. That's the net force. The thing is, we will be doing free body diagrams, and we are only interested in 2 forces. Any force pointing toward the center, we're going to call positive. So when we draw the free body diagram, and if the weight is pointing towards the center of the circle, weight will be positive. If any force is not pointing toward the center, okay? Oops, sorry, we skipped a part. If it's pointing outside the circle, what we mean by that is this force would be positive, but if it's pointing out away from the center, that would be considered negative. All right? So any force pointing towards the center, positive. Any force pointing away from center, exactly opposite to center, will be negative. Any other force pointing any other direction does not take part in net force. So if there's a force pointing over this way, that would not be included in my net force equation. Okay? And so we're going to go through all these different situations of where does it count for net force, where does it not. Okay, we'll do a situation in just a moment to make this really clear. Okay? So that's going to help us create my net force equation, because there's going to be plenty of problems that will be saying solve for the tension, solve for the normal, solve for the frictional force. So we need to make sure we understand where those are going to be coming from. Once we understand that, we can go ahead and create my net force equation. And the thing is, this is not new. That's why the only new formula that you're really getting here is the velocity and acceleration formulas. The net force formula is still m times a. But the thing is, this is now centripetal acceleration. A equals v squared over r. So this is the formula that we jump to much more quickly now when we're solving for net force on a circle. I often write this simply as net force equals mv squared over r. You're going to see me do this a lot in the problems that are about to come up. Okay? So the net force for any object moving in a circle is mv squared over r. Okay? So it depends on the velocity of the object. It also depends on the radius of the object. The larger the radius, the smaller the force. Okay? This last formula, this is one I never use, but this is just the expanded form of the acceleration. All right. So again, what we need to look at now is what is creating these different forces. What's creating the uniform circular motion? Is it tension? Is it friction? Is it gravity? Gravity, we mean weight. All right. Another quick kind of conceptual question that might come up is, what if you have multiple objects attached to one rope? Okay, object 1, 2, 3, and 4 here, all attached to one rope. We could ask a couple different questions here. We can say, what would be the period for all of these? Well, the period would be the same. The period would be the same for all of them because they're all rotating around together. Okay, so there'd be one period. But then we could ask, which object will have the highest velocity? Which object will have the highest velocity? That would be the outside object, because it has the greatest distance it has to cover in the same amount of time as the other ones. Remember, this is 2 pi r over t. It has the greatest radius. Same t, same period, but the greatest radius. So the farther the object, the farther the object is out, the greater the velocity is. So if you're on a merry-go-round and you sit on the outside, you'll be going faster than somebody on the inside. Usually people that feel like they get motion sickness, they stay on the inside because they don't move as much. Okay? I could ask, which object will have the highest acceleration? Well, once again, it's the object on the outside. It's the one that has to change direction the most. Okay? And same thing goes with net force. Which object will have the highest net force? Guess what again? The one on the outside. So the farther out you are on that circle, okay, in these different situations, as long as they're going one speed, will have the most force for all of them. It'll have the highest acceleration. It has the highest velocity. I understand R can play a little bit of tricks with you, but the other way I look at this is, if we draw the vectors, if I draw the acceleration vectors for each of these, this would be the acceleration vector for the first one. This would be the acceleration vector for the second. This would be the acceleration vector for the third. And this would be the acceleration vector for the fourth. Remember, by drawing it, and if we draw the scale like this one is, we can see clearly that the one farthest out has the largest vector, therefore the largest acceleration and force. All right. So before we jump to the practice problem, I want to show you one other thing. I'll show one other thing here. Okay. I want to draw this setup for you. No, let's pick a different color. Sorry. Okay. We will be doing plenty of problems. You'll get plenty of practice of an object spinning in a vertical circle. What that means is, this is standing up. It's like I'm holding this to the side of me and swinging it around and around and around vertically. Okay. So the object is going up and over and then down and around on the other side. It's going counterclockwise here. Okay. So let's say this object is going around and around and around. It's connected to a rope, some little object at the very end of a rope. Okay. Real quickly, let's just go over this fast. Which way would velocity be pointing here? It would be pointing tangent to the left. Which way would acceleration point? Into the center. Which way would net force point? Into the center. Okay? So making sure we always understand that over and over again. I'm going to erase all that. All right. Let's set up our net force equations though now. All right? And we're going to be interested in 4 spots on the circle. It's not going to be perfect. I'm going to draw it out though. Okay, so it looks a little longer down the bottom. Okay. There's going to be 4 spots we're interested in. We're interested in what we call basically the 12 o'clock spot, the 3 o'clock spot, the 6 o'clock spot, and the 9 o'clock spot. Okay? Let's imagine I'm swinging some object by a rope around and around and around on this. And I want you to write out the net force equation for me. What forces would be involved with the net force? So, let's start at the 12 o'clock position. At the 12 o'clock position, what forces would be acting on this object? We're going to ignore friction or air resistance. Well, there's the rope. So the tension would be pulling it down. That's where the tension is. It's connected to the rope. But the thing is, also the weight of the object would be pointing down. So what does this mean? At the 12 o'clock position, the net force for the object will be mv squared over r. I'm going to start writing that out. That's the formula. But what forces will be creating the net force? Well, it's going to be the weight and tension. They're both pointing towards the center of the circle. That means both of them are positive, so this would be T plus W. T plus W. All right? So that's the first one. Now, real quick, as a side note, if I want to solve for tension, what can I change weight into? I can change it into M times G. Okay? M times G. All right? And now if I have M and if I have R, V, I can solve for the tension at the top of the circle there. Okay? So just remember that. It equals M times G. Okay? All right, let's go to the 3 o'clock position. Which way would weight be pointing? Always down. So it's going to be pointing straight down. Which way would the tension be pointing? To the left. Well, let's look at this now. This would still be F net equals mv squared over r. Technically, neither the v or the r should be changing in the problem. The magnitude should not be changing. But what forces should I include in the net force equation? Well, let's look at this. Tension is still pointing towards the center, so I'm going to include tension and it's positive. But weight is pointing not towards or away from it. So guess what? The weight has no factor. It doesn't affect this particular, the circular motion of the object when it's at the 3 o'clock position. Okay? So this would be it. It turns out if you find the mv squared over r, that equals the tension. You're done. Let's go to 6 o'clock. 6 o'clock, weight would be going down, tension would be pointing up. This would be F net equals mv squared over r, which equals, in this case, tension is pointing towards, so tension is positive. Weight is pointing away from center, so now it's minus the weight. Over at the 9 o'clock position, tension towards the center, weight straight down. This would be F net equals mv squared over r, which equals T. And there you go. So you can see, 9 o'clock and 3 o'clock position, the only force, and again, this could be a multiple choice question, what would be the forces acting on the object at 9 and 3 o'clock? The only one would be the tension. At 12 and 6, weight and tension are both involved, but they are involved differently. At 12 o'clock, it's plus W. At 6 o'clock, it's going to be minus W. And so obviously we can think about it. What should that do to the tension? At the top, the tension should be less than the weight because we're going to subtract that number out. Never mind. It should decrease the tension is what I should say. Never mind. It should decrease the tension. At the bottom, we should actually have an increase in tension because I'd be adding this weight to the net force. Up here, I'd be subtracting the weight from the net force. Okay? So sorry. So if I wanted to rank these, tension would be greatest at the 6 o'clock point. It's going to be greater than that at 3 and 9. And then it's going to be the smallest at 12, based on the formula, as long as, again, we're spinning this at 1 speed. Okay? So I wanted to point that out. That's how we're going to be putting these free body diagrams together. And there's going to be a few more problems. We'll go ahead and do those right now. All right? So let's look at some problems here. So I have this 150-gram ball at the end of a string revolving uniformly in a horizontal circle. Ball makes 2 revolutions in a second. This one's just basically going, can you calculate everything? You'll definitely get these problems you need to be able to do. So velocity equals 2 pi r over t. Let's just plug everything in here. It's going to be 2 pi times r, the radius is 0.6, over t. Now is t 2? No, this is 2 revolutions per second. So I need to do the inverse of this. I wanted seconds over revolutions. So what is that? 0.5. Again, one of the biggest mistakes I see students do. If you calculate this all out, it should come out to about 7.5 meters per second. Let me know if I'm wrong if you do it yourself. Okay? Acceleration. Acceleration would be v squared over r. So I now have my velocity, but I'm going to square it. R. What's r? Still 0.6. That will come out to 94.7 meters per second squared. Okay? Acceleration is going to be large because, again, you got to think how quickly is it changing from one direction to another. Very, very quickly. Force. Net force is m times a. This one's not too difficult because everything's given to you. 150 grams, got to change that to kilograms. 0.15 times 94.7, that equals, let me get the answer, 14.2 newtons. Okay? Pretty straightforward there. Next problem. I hit the wrong thing. There we go. Ooh, there we go. All right. The moon's nearly circular orbit about the Earth has a radius of about 384,000 kilometers and a period T of 27.3 days. Determine the acceleration of the moon toward the Earth. So we're trying to do acceleration is v squared over r, but I'm only given r is 384,000 kilometers, which I need to convert to meters. Everything we've ever done, distance has to be in meters. So this is 3.84 times 10 to the 8th meters. The period, it does give me it's 27.3 days, but I need to have this in seconds. So I need to do 24 hours, 1 day, 3,600 seconds in 1 hour. That equals a lot of time. That equals 2, 3, 5, 8, 7, 20. So that would be 2,358,720 seconds. Okay, that's a little bit of time. Okay, all right. So for this one, this is a good example where you could go ahead and try to use that expanded formula for acceleration, but me personally, I just find the velocity. I do 2 pi times 3.84 times 10 to the 8th divided by 2358720. I find the velocity first, which gets me 1,023 meters per second. That's actually how fast the moon's moving around the Earth. And then I just solve for velocity by squaring it, dividing by radius. 1,023 squared over the radius again, 3.84 times 10 to the 8th. That equals 2.72 times 10 to the negative third meters per second squared. It has a very large circle to go on, so the acceleration is very, very small. Okay? Very large radius. All right. Very good. Next. I keep on hitting that button. All right. This one finally gets to a more tricky circular motion problem. Okay. So this one, we have a 0.15 kilogram ball on the end of a 1.1 meter long cord swung in a vertical circle. Determine the minimum speed the ball must have at the top of the arc so that the ball continues moving. So this is a very important question, a very common question. What is the minimum speed it must have at the top of its arc? Okay, I'm not even going to look at B yet, so it can complete the circle. All right, so I'm going to take us back here again. So it's basically similar to the diagram we just did together, where it's going around in a circle, okay, and it's at the very top of the arc here. And so we know the tension, it would be pointing down, the weight would be pointing down. And so I can sit here and go, okay, F net equals mv squared over r equals tension plus weight. All right, let me go back and see what we're given again. We're given mass and radius. This would be the radius, and obviously we have the mass here. Okay? And I'll explain why I don't use a different formula. I'm going to use this formula. Okay? So radius was 1.1 meters. Okay? And the mass was 0.15 kilograms. All right. So I can see some people going, well, you're asking for velocity. Why don't I use this formula? 2 pi r over t. I have the radius, but you have nothing for time. There's no way to solve for time, so this formula is out. It doesn't work. Okay? So we can't do that formula. So what we have to go to instead is the only other one that has velocity in it is the net force formula. Okay? Or that we can use it. Obviously we can do acceleration, but again we don't know acceleration. So for this, we have to go to the net force equation. All right? And so the thing is, you might still sit here and go, well, I don't think I still have enough information. I have m, I have r, I can find W by doing mg, but what the heck is T? Well, that's the important part. That's the key. It's asking for the minimum speed to complete the loop, to complete the circle. All right? Well, what that means is T equals 0 newtons. The string is still there, but it's no longer pulling it. If I get rid of, I can decrease V by decreasing the forces on this side of the equation. I can't change the weight of the object though, so that one I can't decrease. But I can decrease the tension all the way to 0. And that is a very common thing that's going to come up. We're going to do another problem where you'll see normal force go to 0. Weight can't change. Weight is there. The object has weight. But I can have absolutely 0 tension in the string and still make it go in a circle because the weight still points towards the center of the circle. It will still cause it to change direction. So what that means is, it leaves me with mv squared over r equals the weight. I set t equal to 0, I get this equation. That gives me mv squared over r equals m times g. Well, guess what? I don't even need the mass of the object. This is a worthless piece of information. It's not necessary. So that leaves me with v squared over r equals g. V squared r equals g. Sorry, I'm going to go to the left. V squared equals g times r, and v equals the square root of gr. This formula right here will be your minimum speed formula. Now, it will not be given to you, but you should recognize that you get to that formula whenever you do these problems. All right? And again, this is a very common problem. We're going to be doing roller coasters. We'll be doing cars going over hills. Okay? This formula will come up every single time. It's asking you what's the minimum speed that you can go to still stay on the ground, or so forth, or still complete the circle. And so now I can complete this problem. V equals the square root of gr. Oh my gosh, it's become a pretty easy problem. 10 times 1.1, take the square root of it, and the speed that you can go to complete the circle is 3.3 meters per second. This would be the minimum speed the object can go, and it'll still complete a whole circle. Okay? So this formula is very important. All right, part B. Part B, calculate the tension in the cord at the bottom of the arc. At the bottom of the arc, assuming the ball is moving, pay attention, twice the speed of part A. So it was going 3.3 meters per second, so now it's going 6.6 meters per second. Okay? So 6.6. All right, so let's go back to the problem. So now I'm looking at the bottom of the circle. That means tension points up, weight points down. Velocity is 6.6 meters per second. All the numbers are still the same, 0.15 kilograms. Radius is 1.1 meters. 1.1, right? Yeah, 1.1. All right. Down at the bottom, we have to have the tension. Tension can't go to 0 because then we'd only have forces pointing outside the circle, and that doesn't work. So we have to keep the tension. But it gives me this equation. F net equals mv squared over r equals t minus the weight. So t will equal mv squared over r plus the weight. And so then I plug everything in. 0.15. This time I need the mass because I'm solving for a force. 6.6 squared over 1.1 plus 0.15 times 10, m times g. 10, sorry. Okay. And this comes out to 7.44 newtons. 7.44 newtons. Okay. So the tension is larger, obviously, always on the bottom. All right. Two more problems. Almost done. This is a pretty long one. Sorry for, you can obviously pause if you need to at any time. Okay. All right, question 4. 1,000 kilogram car rounds a curve on a flat road of radius 50 meters at a speed of 14 meters per second. Will the car follow the curve or skid? All right, so this is another popular problem, the skidding problem. Okay, so what we need to think here is you're going around a curve on a road. Here's your car. You're looking from top view down. Okay? You're looking down on the object. This is from up high. You're in a helicopter. All right? What forces would be acting on this car? Well, you could say weight, but weight would be pointing into the screen. Because again, you're looking from top down. Normal would be pointing away from the screen. There would be frictional force going back, but the thing is, what's pointing towards the center? That's the question. What is pointing towards the center? Well, it's a force that's hopefully preventing you from skidding out. So what force helps you prevent motion, to try to stop your motion? Well, guess what? There's another frictional force pointing towards the center. There's actually two frictional forces. This is kinetic friction because you're moving, and it doesn't affect the motion because it's pointing away from the circle. But this would be static friction because the idea is you haven't started sliding yet. So this is a static frictional force. All right? And so what we need to do is a couple ways to solve this problem. Okay? What we need to do is it's asking, okay, based on this speed, will you skid out at 0.6? When the coefficient of friction is 0.6. Will you skid out when it's a lot less, when you're on an icy surface and the surface is 0.25? Okay? So I'm going to show you how I like to solve it. If I have time, I'll try to solve it the other way that I know students like to solve it as well. Okay? So the way I like to solve this is I like to do it in one step, basically, and then compare. So this object's going around the circle. Force towards the center is frictional force. So guess what, guys? Net force equals mv squared over r is just equal to the frictional force. That's it. That's the only force involved. It's okay to have only one force. The thing is, where does mu show up? Well, you're on a flat surface. So remember, frictional force equals mu times n. Mu equals frictional force over normal. All right? Well, if you're on a flat surface, the normal force equals the weight. So this could be frictional, this could be, let me rewrite this. I'm doing this kind of a silly way. I didn't need to change it from this. Leave it as my first formula. Frictional force equals mu n. So this would be mu times W, which would then equal mu mg. So now you have an equation of mv squared over r equals mu mg. This would be your starting point for any skidding problem. I'm trying to solve for mu. What I'm about to solve for is the minimum mu that you need. This will be the minimum coefficient of friction to prevent sliding, to prevent skidding out. So let's see what I have here. I need to go back and get all my numbers. Okay? Now it gives me the mass of the car, but what do you notice? Mass cancels out. Oop, pressed the wrong thing there. Mass cancels out. Okay? Let me go ahead and derive this equation. This leaves me with v squared over r equals mu g. So mu will equal v squared over gr. So I only need the velocity and the radius. Obviously I can plug g in. So the car is going 14 meters per second at a radius of 50 meters. Okay, so let me plug that in. 14 squared over 10 times 50. And that gives me a coefficient of friction of 0.392. What this is this is the minimum coefficient of friction I need to make sure I don't skid out. If the coefficient of friction is greater than this, I won't skid out. If it is less than this, I will. And so if I go back to the problem, my coefficient of friction is 0.392. Well, this is greater than, so this one will not skid. I will not skid out on dry pavement. But this one is less than, so I will skid on the icy pavement if I go this fast. Okay? The other way to solve it, I'll let you guys play with it if you want to, is basically go ahead and calculate the numbers out. Find the net force, do mv squared over r, and then calculate mu mg with both of these. Okay? If it comes out greater, then guess what? You're not going to skid out. If it comes out less, you're going to skid out. Okay? That's basically what you're looking for. Okay? Because the net force, this is basically saying this is the minimum frictional force that you need. So if it doesn't come out, if it comes out less than that, you're going to skid out. And so that leads us to our final problem. All right. You're going over a 2,000 kilogram car, goes over a hump that has a radius of 25 meters. Hey, look at this again. What is the minimum speed at which the car can leave the road? Okay. What's the minimum speed where now the road will still be touching the car, but it won't actually be pushing the car at all? Okay. So 2025. Okay, here we go. So let's look at this problem. What you're doing now is you're on the top of a hill. Draw in your free body diagram. Weight down, this time normal up. Okay? So that'll leave me with a net force equation of weight minus normal. The hill we consider to be basically a continuation of some giant circle that we don't ever see. All right? But the thing is, it says, what's the minimum speed? What's the minimum speed? Well, guess what? That means normal goes to 0. And so now I can solve my problem. mv squared over r equals mg. Hey, look at what's going to happen. M cancels out. V equals the square root of gr. Okay? And so therefore I do the square root of 10 times 25. And I get a velocity of, I think, 15.8 meters per second. 15.8 meters per second. I think that comes out just fine. Yeah. Okay, 15.8 meters per second. All right. So same exact idea. Same exact idea as that the third problem we did. The minimum speed to stay on the hill but without leaping would be this right here. If you go any faster than this, guess what? You're going off the road. All right. I think we got one more problem. If the car is instead going through a dip at the velocity found in A, what would be the normal force the car feels? So now we're just reversing this. Now you're going through a dip, so you're at the bottom of the circle. That means weight's down, normal force is up. That gives me net force equals normal minus weight. I want to solve for normal force. Normal will equal F net plus W. So this is mv squared over r plus mg. Let's plug everything on in. Let's plug everything on in here. Sorry, the number's 2025 again. So this would be 2000 times 15.8 squared over 25 plus 2000 times 10. And I get an answer of 39,971 newtons. Okay. And again, if you feel like I make a mistake, always just let me know. All right. So that's it. Those are circular motion, directions of acceleration, velocity, and force. Draw out a free body diagram when you're doing these problems. And from there, look at what cancels out and solve. All right. Thank you very much.